first thing that comes, that is, what is circular motion? So by definition, circular motion is, we can call it any motion that is taking place along a circular path. Motion in a plane means any motion that is taking in a plane. Motion in a straight line means any motion that is the motion is happening along a straight line. Now circular motion is the motion is happening along a circular track or circular path. Now depending on its speed, like how the object or how the particle is moving on along the circle, how its speed, and that it's mainly categorized into two types. One that is called uniform circular motion, other one is called non-uniform circular motion. So first, what is uniform circular motion? So uniform circular motion tells us when an object moves in a circular motion with constant speed. During the motion, the speed has to same. That means when it moves with constant speed, that means it covers equal length of arc in equal time, right? It moving in a circle with same speed is not changing. That means in equal time interval at delta t time, if it moves from this arc, for another delta t time, it will move the same distance of same length here. It will also, for the same time interval, it will cover another same distance. That's what we call for uniform circular motion. For non-uniform circular motion, it's like same. We can follow the same analogy of the uniform circular motion. This time, the motion is happening along a circular path, but the speed is not same. Speed can alter. For suppose for 1 second the particle can travel this distance here. For here it can cover for 1 second is a large distance. Here it can cover another large distance. I'm just assuming it can cover. The point is, if for uniform circular motion, for unit second or for same time interval, it covers same length of arc or the same length. As for non-uniform circular motion, it covers different length in same interval. And because of this comes from the fact that uniform circular motion is the motion with constant speed. Non-uniform circular motion is motion with a non-uniform speed or different speed. So can you tell me some household example of uniform circular motion and non-uniform circular motion? First, start with uniform circular motion. What can you see around you, or what have you seen around you that is falls under uniform circular motion? Okay, fan, clock, good. The analog clock. Okay, so these two, I think if I were you, I would have gotten the yes. I would have given the same answer. I mean, if my teacher asked, I would have been the same these two answers, because these two are the one that is most probably right now I'm saying. One that is fan, other one that is a analog clock. Now, regarding fan is not actually, this is uniform. I cannot say it's always uniform, because when a fan moving with constant speed, in that case I can say it's uniform. But fan can be, there are sometimes like just the moment the switch is on, in that case fan started motion, and for some time or for 1 or 2 seconds it reaches a maximum speed or some particular speed. So during that time interval, its speed is not constant. So fan can be in case of both. It can be uniform circular motion, it can be non-uniform circular motion as well, depending on which time you're pressing. If we consider that just the moment the switch is on, that is also non-uniform circular motion. If we consider the fan was supposed to be moving at a constant speed and I'm just switch off the fan, in that case the motion retarded, right? It was moving and then come to rest. So in that case, during that interval, it also falls under non-uniform circular motion, because its speed started to decrease. When the switch is on, its speed started to increase. When the switch is off, speed started to decrease. Apart from that, any motion what I'm trying to say is, if the fan is moving with like constant revolution or constant speed, that's uniform circular motion. But fan can be also an example of non-uniform circular motion for particular these two instances, when the time switch is on, when the switch is off. Another, if I say analog clock, an analog clock with a normal battery move with uniform speed. But sometimes, if you must have seen that when the battery get reduced at the end of the lifetime of a battery, the clock does not perform well. In that case, what happens, you will see the second hand will take less time to move from here, like move from 12 to 6. It will come very fast, but it will take very less or more time to move from, and sometimes it may not even cover the whole thing. It gets stuck sometimes. I'm only considering the when the battery life gets reduced. How many of you noticed that? Or I think none of you have noticed, because you have all moved in the analog one. Sorry, digital one, because right now these days analog clocks are kind of ancient. Not ancient, like antique. I'm still using analog clock, but sorry, yeah, analog clock. But if you are seeing a digital clock, so this factor may not come. So my point is, for a normal clock, when the battery is at full or the battery is in optimum state, we can call it, it's a uniform circular motion. But when the battery get reduced or the end lifetime of the battery, that is not actually uniform circular motion, because at that time we can say that it's not performing well or it's getting slow. It's getting slow in that sense. It's not like that state, the minute hand or the second hand, they are not revolving properly. So that's another example of non-uniform circular motion. Is this okay what I'm trying to say? And of course, there are some, if we go for a bit more than household, in that case, there are lots of the example, that is the motion of planets, Earth's own rotational motion around its axis. These are all falls under uniform circular motion, because, well, to be precise, it's not actually uniform, but anyway, in broader sense, you can call it uniform circular motion. Circular motion will have a like detailed study in case of rotational motion, but this one they introduced just circular motion just to introduce the centripetal acceleration, or just they want us to tell, or they want us to know that even though the particle can, I mean, in uniform circular motion, what happens? In uniform circular motion, the object move with constant speed, but they're just a point of introduction that even the particle moves with constant speed, it can be associated with some acceleration, and that acceleration we're going to study here. But the actual where this is comes from, that we are going to learn in next chapter, that is motion in a plane. And the more detailed study of rotational motion will be studied in the chapter of rotational motion and system of particles. So actually the one concept has been broken into three pieces. This is just the introductory part, that is there is an acceleration associated. Where does it come from? This will be studied in the next chapter. And the more detailed analysis, like what the real life uses, what are the other types of rotational, and these are the things will be discussed in the another chapter. So let's start with discussion with uniform circular motion. First we discuss with uniform circular motion, then we move to the non-uniform circular motion. So uniform circular motion, by definition, it has to move with constant speed. During the motion, the speed does not change. Also, it covers equal distance or equal arc in equal time interval. Okay. So if I ask you, a particle is moving along a circular path at any instant, what is the direction of its velocity?
Tangential.
Yes, at any point along the tangent. At different point, the velocity points along tangent direction. Okay. So what I'm trying to say is, even though the particle or the object moving with constant speed, as it moves, the direction of the velocity changes. Here it was in this direction, here it is in this direction. And because of that, since there's a velocity, because acceleration associated with the change in velocity, not with change in speed. And the velocity is a vector quantity, so it has some associated direction as well. So since the direction is changing, it will have some associated acceleration, which is called in generally, that is centripetal acceleration, or centripetal in that sense, center seeking, or this acceleration points towards the center. Now, I am taking an example. This is a object that is moving in that direction, I mean, in a circular path. At every point, the velocity vector points in the tangential direction, and because of that, there is the acceleration. Now, there is acceleration. We have proved this fact when you study the motion in a plane. We took some example, and we saw that even though the particle moving in I mean, we did an example before, long before, that is during the motion in a plane, that is a particle moving in a circular path, and we have shown in both in unit vector notation as well as vectorial notation that there is an acceleration associated with it. But this time we are going to be more details and more precise to find with the what is the acceleration's direction, as well as what's the magnitude is. So if a object is moving with this constant speed u in along a circular path of radius r, the acceleration or the centripetal acceleration has a value of v square by r, and its direction is always towards the center. And since the direction is always towards the center, it's called centripetal acceleration, or in some sense it's a center seeking acceleration. Sir Isaac Newton pointed this name, or the centripetal part. So now from the rotating figure, we can point out two things. Well, not just two things, there's a few things. That velocity is always towards the tangent or in the tangential direction. Acceleration is always towards the center. Okay, so this tells us that for a uniform circular motion, the acceleration vector and the velocity vectors are perpendicular to each other? Yes or no? I cannot stop the figure, but you can see from the figure that any time those two vector makes a 90-degree angle. Now, if I ask you, look at the figure and tell me what is the velocity vector makes an angle with the position vector. Let's consider the center as origin. So at any instant, the angle between position vector and velocity vector. Okay, one said 90-degree. Anyone else? Okay, so what's happening? If I draw another one, because I cannot stop that figure. So here we are considering an origin. At some instant, suppose the object is here. So at this instant, its velocity along this direction? No, not 0. Look at very carefully. The radial vector or the position vector is kind of this, because this is the position, this is the origin. So what is the angle of R and V? 90-degree, right? If we shift this vector V here, the angle between them is 90-degree. So the angle between the position vector and the velocity vector is 90-degree. Okay. What about the angle between radius vector and the acceleration vector? Think, you draw a figure and then tell me what you got. Okay. Somebody said 180. Anyone else? I mean, this does not actually require from previous concept, right? This is just a simple concept of vector. So I don't think like why you are all silent. This is just a simple question I'm asking. There is no need to like, this is not require of any deep concept or anything. Just look at the angle. Angle we have studied in case of class 7, I guess. Okay, I guess nobody. Okay, so basically suppose at some instant the object is here at point P. So the position vector is in this direction. The acceleration vector is towards the center. So basically one vector is away from the center, one vector is towards the center. So basically this is our vector R, this is our vector A vector or acceleration vector. So the angle between them is 180 degree or pi. Make sense? Okay, so these are the thing we did find from uniform circular motion, that the velocity vector always perpendicular to the radial vector or position vector. The velocity vector is always perpendicular to the acceleration vector, and the radial vector or position vector at an angle 180 degree with respect to the acceleration vector. Okay, now these are the thing we have actually just stated the fact, that is, I have said the acceleration has a value of v square by r. I have also said the acceleration value it points towards the center, but I haven't said any solid proof on any of that. I haven't proved this one. I haven't proved the direction as well. So that's the question that is like, there are two questions that still bugging us. That is, where did he get this value acceleration is equal to v square by r, and where did he get the direction that is it will point towards the center? So let's do both. That is, first we will see its direction, then we'll find out its value. So the direction of the centripetal acceleration, what does point? So let's consider an object that is moving with a speed v, that is constant speed, along a circular path of radius r. Okay. So what happens? Let's take two different instances. At two different instances, the particle or the object is located at 2 points, that is at point P and it is point Q. Can you see that? The point P and Q. Okay. Also at those two respective points, it has a, at point P it has a position vector of r, at point Q has a position vector of r prime. At point P it is a velocity vector v, at point Q it is a velocity vector of at point Q it is a velocity vector of v prime. Now v prime and v, they have both magnitude of v because the motion is taking along a speed v, but since it's a vector, so it's basically different because they have different direction. Okay, yes or no? Okay, so let's don't focus on the other part, that is delta theta delta. Don't focus on there, just focus on point p and q. Those two have different position coordinate of, not position coordinate, position vector of r and r prime, and the respective velocities at p and q will be v and v prime. Okay, now if I ask you to move from p to q, what is the direction of average acceleration? So what is the average acceleration? Average acceleration is given as the change in velocity per time, right? And also we, in the motion in a plane study, we have seen the average acceleration has the same direction in the direction of change in velocity. I mean the direction along which the velocity changes, the same direction the acceleration points. Yes or no? We have taken example. I mean those who have attended the class, I think no. As per Gungun, Harshita, I think you will know. Yeah. So, and as for the rest who don't know, that there is, it is a fact that is acceleration always points towards the direction where the change in velocity. Now delta v means the change in velocity, and delta v always referred as, that is final velocity, that is v prime minus the initial velocity v. So the direction along which delta v points, the same direction will the average acceleration will also points, right? Okay, so just by minor adjustment we can write it. If we want to try to find the direction, we have the direction of v and v prime, right? We'll try to find the direction of v. You can just a bit of minor adjustment, that is v plus delta v is equal to v prime. So if we take v plus delta v is equal to v prime. So if we take the triangular part, that is we just, here is v, right? Point p. Okay, if we shift the vector v prime here, this is our v prime. Okay, so delta v will be along this direction. Use the triangular law. The triangular law from this triangle, you can see v vector plus delta v vector is equal to v prime vector. Yes or no? So what is the direction it's pointing? Delta v towards the center. So I have a better figure here. I can write it as, draw as this. That is delta v, which is the difference between v prime minus v. This relation, that is delta v is equal to v prime minus v, and the direction is still points towards the center. Okay. Now, as for point P and Q, suppose we take another point, that is at point X, where the velocity is, suppose this is a point X, and the velocity we have v double prime here. Okay. So in that case, we'll also find that is delta v, which is simply we have v double prime minus v, the change in velocity from P to X. Okay. So what happens if we shift vector v here, the velocity vector, in a larger pane, I guess. So this is our v double prime vector. The direction of acceleration is delta v. So delta v points towards the center. Yes or no? Okay. So here we have considered the point X. Not just that, we can consider any point, any close point. If we, again we can consider point P, we'll still see that it's in the towards the center. If we see very two points that is very close. Now for larger distance, for point P and point Q, we have A average, because it's a long time from P to X. It is again average acceleration because it takes some time to cover this distance. But what if we consider a point that is very close to P? So if we consider a very point that is very close to Q, that is we are considering 2 points, that is P and P prime, that is very close. So P and P prime are almost close. Now almost close, that means the time to move from P to Q will be very small, that is dt. So in that case, what happens? The average acceleration converted into instantaneous acceleration. But the point it still points towards the center. So average acceleration as well as instantaneous acceleration, they're both points towards the center. That means if a particle moves along a circular path, the acceleration at any point, the instant acceleration at any point always be towards the center. Make sense? For whom it did not make sense? It's just that we're using the fact that is acceleration has the same direction as delta v, the change in velocity. Now, change in velocity is simply we have the final velocity, that is v prime minus our initial velocity. This is always remember, that is change means final minus initial, not the other way around. So, and that we'll use the triangular method or any vector addition or vector subtraction, anyway you can say. And we just need to find the direction of delta v or the change in velocity. And change in velocity has the same direction as acceleration, which we saw for taking multiple examples that they're all points towards the center. Okay. So one fact that we got, that is direction of acceleration is towards the center or towards point O. Okay. Yes or no? So one part we got clear, that is the direction is always points toward the center. Next part is how did we get the value of v square by r? Okay. So this one we need to derive, that is how do we get to find the value that we have? The acceleration has a value of v square by r. The object is still moving with a speed v. The two different point has same thing. I'm saying it, point P and point Q, and the respective vectors are r and r prime. The respective velocities are v and p prime. And we need to find the value. Now this time we need to resort some trigonometry, basic trigonometry. Okay. So let's assume that from point P to Q, object takes time delta t to move from P to Q. Also, it covers a arc length of delta s. This is the arc distance of along the square, sorry, along the circle. Okay. Yes or no? I'm just assuming this fact that it's moving with a constant speed v. To move from point P to Q, it covers a arc length of delta s in a time of delta t. Now, velocity vectors and position vectors are shown. Now, look at the triangle, that is triangle OPQ and triangle ABC. Triangle OPQ are the triangle made by the position vectors. Triangle ABC are the triangle made by the velocity vectors. Okay. Now, I am saying that these two are similar. Now, then you will tell me, like you will ask me, like, how can we say that? Or can we even say that at all? That is, are they even similar or not? Where did you get this value? Like, why did you say it is similar? Okay, so similar in that sense, both triangle POQ and triangle ABC, they are isosceles triangle. That is, they have both two arms are equal. For OPQ, there are two position vectors that are same because both are radius. For triangle ABC, we have two arms that are same. That is formed by V and V prime. But since they're vector, but their magnitude are same because they both have magnitude of V. So both are isosceles triangle with two arms are equal, but similar in that sense. I mean, they are both isosceles triangle and the angle between them will be same. Now, how can you say the angle between them is same for both of them? Can you even say that? Can you remember the example we have taken in the motion in a plane case, that for 2 points, the angle between the velocity vectors and the angle between the position vectors are same? Harshita, you were saying something. I just interrupted, I guess. Okay. So even if we just neglect everything, let's consider 2 points. Here I am taking, okay, I'm taking point M here. I'm taking point N here. Okay. So point M is the velocity will be along positive x-axis. Along N, the velocity will be along positive y-axis. Okay. So what is the angle between these two velocities at point M and point N? They are perpendicular because one is along x-axis, one is along y-axis. Okay. What is the angle between the position vector of these 2 points? This is the position vector there. So again, the angle is 90 degree. Okay. If we take another point here, that is, let's take a point Q here. So here the velocity vector will be along negative x direction. So in between point M and Q, the velocity vectors are in 180 degree. The position vectors, they are also 180 degree, right? So I have taken only symmetrical cases, but you can take any 2 points and you will get the same fact that the angle between the position vectors, that means the angle between these two and the formed by the velocity vectors at those 2 points, they are same. Is this okay? We have proved this in the study of motion in a plane, but since most of you have missed the class, I guess, so basically I just have to say it again. So this is kind of, so now we can say the triangle of OPQ and the triangle ABC are similar. They are both isosceles, and the angle between them are same. That is delta theta. Okay. Yes or no? Okay. Now take both triangle. From this triangle, I mean using these two triangle, I can write it as delta V by V is equal to delta R by R. Can we write it? Okay. So this is the fact we got. Okay. Now from P and Q, since they are very large a distance apart, that's the reason I can say this is delta R and delta S has a different value. But suppose P and Q are very close. This is if the Q point was there. In that case, the value of R and delta S, delta R almost equals to delta S if the point P and Q are close, right? For long distance, we can see it as a curved path, but for smaller distance, the curve is almost equal to a straight line. So that's going to use the same fact here. That is delta V by V is equal to, we'll write it as, replace it delta R by delta R as delta S. So this is another relation we got. Okay. Now the rest part is kind of geometric or algebra, you can tell it. We will find this is V, which is the value of V is will be our V by R into delta S. The point is we need to find the value of acceleration, right? Acceleration is del V del T. The particle point take from P to Q to this time of delta T. The acceleration will be del V by del T. So that's the we're trying to point out, that the value of acceleration. That's the reason we find the delta V. Now we take both side by delta T. So del V del T gives us V by R into delta S by delta T. Is this clear to this point? Dividing both by delta T. Okay. So del V del T, this represent acceleration, right? And more specifically, it represent centripetal acceleration in circular motion, but I'm representing it acceleration. Acceleration is as V by R and del S by delta T. The particle was moving with a speed V. If it covers a distance of delta S during delta T time, so basically del S by del T is also the V, right? Yes or no? So del S del T you can write as V. So V into V by R, so it is give us V square by R. So finally, this is write it as this acceleration is simply you have V square by R. Okay. So we also got the value as well. In the previous slide, we got the direction. In this slide, we got the magnitude. So both of the answer or both of the question regarding centripetal acceleration got solved. That is, It's always towards the center, and it's always has a value of v square by r. Okay. Any confusion? Okay. This part was kind of unnecessary, but the direction part, like that part, like some of you may be wondered, because in my time I wondered that what's the direction, why the direction is towards the center. But this is part like not need, don't ask the derivation part. But anyway, since we are doing trying to answer this, so it's basic to know what the basics we are dealing with. Okay. Next is, this is circular motion. Circular motion is the first step of regard or relating some linear quantities with angular quantities. Because if a particle move from point P to Q, it covers a linear distance of delta s, but it also covers an angle of some angle, right? According to this figure, it covers an angle of delta theta. So in linear way or in linear method, if a linear in that sense, like it's a meter or some normal distance, so normal speed from P to Q is delta s by delta t, right? But similar way, we can define an angular speed. Angular speed, that means the how much angle it's covering in unit time. The linear speed is how much distance it's covering in unit time. Angular speed is how much angle it's covering in unit time. So it covers an angle of delta theta in time delta t to move from P to Q. So angular speed is usually defined as omega. So omega is given as the angle covered by unit time, or more like the change in angle in unit time. Okay. So the uniform circular motion, the first step in that sense, this is the we need to find relation between V and omega, how they are related. Okay, it's kind of simple. So what is V is equal to delta S by delta T, right? So delta S by delta T, using this figure or using the trigonometric notation, what delta S we can write? Delta S, we can write it as r delta theta. That is the radius, because arc is, or more like angle is r per radius, right? Delta theta is equal to delta S by r. So delta is equal to r delta theta, and we have time, that is delta t. We know the angle theta is simply we have arc per radius, right? So theta we have delta theta, arc length we have delta s, radius we have r. So the same thing I written as, that is delta s is equal to r delta theta. Yes or no? That is why I'm writing here, right? The arc length. So we'll just do a bit of adjustment, that is r into delta theta by delta t, and delta theta by delta t is simply you have omega, so it's basically r omega. Okay. So that is the relation of linear speed and angular speed in case of uniform circular motion, or more like in circular motion, that is linear speed is equal to radius into angular speed, or we can again write it as angular speed is equal to linear speed by radius. They are both applicable. This is the relation in between them. Okay. Centripetal acceleration, that is a value of we got, that is a value of v square by r. It can be also represented in terms of angular speed, that is v we know r omega, so can we write it as r square omega square by r. So it gives us r omega square. So this is a representation of centripetal acceleration in terms of angular speed. It's some kind of, we can say it's a kind of alternate expression. Okay. Okay, let's move to the next part. This is the relation, that is angular quantity, and regarding that, that is there is also a kind of relation. There will be details in rotational motion, that is a angular acceleration and some others part. So that's not included at this point right now. But this is just the relation of as I mentioned, this is the first step, because this whole thing has been distributed into 3 chapters. So this is the first step in that sense. Will just gonna be introduced in relation between linear speed and angular speed. Next is, there are 2 other quantities that is very important regarding frequency and time period of a circular motion. in any circular motion, it's like not just circular motion, there are some oscillation as well that we are going to learn in oscillation chapter. But if it's a circular motion, there is always two associated quantity, that is one is called frequency, another one is called time period. So let's start with time period. So what is time period? Time period is defined as the time taken by the object in one full rotation. That means suppose a object is moving in a circular motion, it start from point A, after a whole rotation, it returns to point A. So the time it take, or the total time it take to move from A to come back to A again, is called time period. Okay, and since time period is simply a time, so basically it has a unit of second. It's a dimensional formula of t. Next is what is frequency. Frequency is also related to the time period. That is, time period is how long it's taking to come back to same point. Frequency is defined as how many full rotation is doing in 1 second. Time period is how long it's taking to move one full rotation. Frequency is how many rotation is taking in one full rotation. So just by intuition, you can tell F is equal to 1 by T. They are kind of opposite. Okay. So this is the relation, that is frequency and time period, they're related as 1 by T. Okay. Now frequency has a unit of common unit that is called hertz. Okay. It has another call unit that is called CPS. CPS means cycle per second. It sometimes has another unit called RPS. RPS means rotation per second. It can also be sometimes as CPM. CPM in that sense, circle per minute. It also be sometimes written as RPM. RPM in that sense, rotation per minute. Similar way, CPH, circle per hour, RPH, rotation per hour. But in generally, CPS and RPS, they are both considered as hertz. Hertz means how many, how many rotation or how many one full oscillation they are taking is 1 second. Okay. So if we consider a circular motion, suppose a particle moving from point A, returning point A, how much total angle it's covering? From point A to B, it's covering a total angle 360 degree. So from A to A again, it's covering an angle of 360 degree, or you can write it as 2 pi. Okay. So how much time it's taking to cover if the particle is moving with a speed of omega? So how long it's taking to cover this whole 2 pi distance? That is time taken, that is 2 pi by omega. Because omega is related to how at which rate this angle is covering. So its total covering angle is 2 pi, and we can write it as, it's like more like we can write it as covering an angle. So angular velocity or angular speed is omega. So the time period or the time taken to for a full coverage, it's called 2 pi by omega. We can take it as another way. To cover the whole perimeter, how much linear distance it's covering from A to A? 2 pi r, right? Yes or no? From A to A, the linear distance is covering 2 pi r. The speed is v. So 2 pi r by v, that's the time period. We can write it as v as omega r. We have just previously we have find this relation, v is equal to omega r. So this relation is also tells us that is t is equal to 2 pi by omega. So time period has a two form, that is 2 pi r by v, as well as it has a time period of 2 pi by omega. Okay. Now that we have time period, we can have the frequency relation, that is 1 by t, which is omega by 2 pi. Yes. Okay. And now this is the thing we have found. There are some other related quantities that can be expressed in terms of angular quantity. That is the first thing that we have seen, that is v, or the velocity or linear speed. That is, from this expression we can write it as the this expression, we can write it as 2 pi r by t, right? Now 1 by t is f simply, so we can still write it as 2 pi rf, where f is the frequency. This is the gives us a relation of frequency and linear speed. Okay, next we can write it as omega with respect to frequency. Now omega is equal to v by r, so it's basically 2 pi f. V by r, v we got 2 pi rf, so omega is 2 pi f. This is the relation that gives us the angular frequency and linear frequency and angular speed. Now some other chapters will learn that angular speed and angular frequency kind of same thing. So this is also relation that gives us the relation between angular frequency and angular speed. I'm not introducing the angular frequency yet, but just to know, this is the relation between angular speed and linear frequency or frequency. This same relation is applicable for angular frequency as well as linear frequency. It's just a kind of spoiler, you can say. Okay, next we can write it as centripetal acceleration, which is we have v square by r or omega square r. So just put the value omega value we have 2 pi f, so it will be 4 pi square f square r. So direct some question, sometimes the frequency is given indirectly for a circular motion. If the speed is given, if the radius is given, you can always find the acceleration, centripetal acceleration. But sometimes directly speed is not given, the frequency can be given, the radius is given. So using this relation, you can find centripetal acceleration. Okay, now these are the relation, that is v, omega and acceleration in terms of frequency, right? The same thing can be done in case of time period as well. To find that, we just have to put f is equal to 1 by t. So omega can also be written as omega is equal to 2 pi by t. That is one relation. Right, centripetal acceleration AC can also be written as, we'll just have to put f is equal to 1 by t. So this gives us 4 pi square r by t square. So that is another way. So basically, sometimes they just put through, like instead of giving directly, they just group some, like try to like put it in a loop or something. Anyway, just try to confuse us. So these are some another cases. Okay. So uniform acceleration or uniform circular motion is up to this point, but there is another part, that is a counterpart, that is non-uniform circular motion. So non-uniform circular motion, that is in uniform circular motion, during the motion speed wasn't changing, it was covering equal arc in equal time. But this time the speed is changed. Since the speed is, if the speed changes along its motion, it's called non-uniform circular motion. So basically in non-uniform circular motion, the speed of the object at different point changes. Okay, now speed change means it covers different kinds of distance in different time. Suppose this, I'm taking 4 point A, B, C and D. If we compare point A and D, at point D has a large velocity or more like large speed, so at point D it will cover more distance compared to A. So basically, if the speed changes, the covered distance it also changes. Okay, so now put the analogy here. In case of in uniform circular motion, the v was constant. Okay, the acceleration was came because of the direction changes. This time the speed itself is changing. I mean, the velocity vector in uniform circular motion was changing due to only the direction, but this time because of circular motion direction changes, and because of this speed change, there is, I mean, speed also changes. So basically non-uniform circular motion, we can call it the two kinds of acceleration. One acceleration is centripetal acceleration because of circular motion, because any kind of circular motion will have centripetal acceleration because the direction of the velocity vector changes. And this one, since its velocity is changing, in that sense, velocity is always a tangent direction. So if the velocity change in the tangent direction, there is a tangential acceleration we got, that is usually defined as at. So because of speed change. In uniform circular motion, only AC was there because there's a no change in speed. But this time, since the speed is changing, so there is another acceleration because of, you see, if a particle motion in a straight line and acceleration in this direction or in this direction, so the speed changes, right? Similar way, this one is if the speed changes, so there is a acceleration associated in this direction or the direction of velocity. Okay. Centripetal acceleration does not change speed. Centripetal acceleration only changes direction. This part will be cleared when we discuss about the where does acceleration come from. Acceleration comes from a force, and similar to a force that is called centripetal force. So because of centripetal force, there comes a centripetal acceleration. That part is later, but if we consider only centripetal acceleration, because of centripetal acceleration, speed does not change. Centripetal acceleration lies in uniform circular motion, where we have seen there is no change in speed. But this time, because of centripetal acceleration, there is no change in speed, but because of there is a speed change, the particle moving along different speed at different points, there is another acceleration that is called tangential acceleration. Okay. Basically, you can take it as this way. Uniform circular motion, there is only direction changes, and because of the direction change, there is the acceleration that is came into factor is centripetal acceleration. In case of non-uniform circular motion, there is a two counterpart. One, because due to the direction change of velocity comes centripetal acceleration, and because of the speed change part, there comes another acceleration that is called tangential acceleration. Tangential acceleration, in that sense, the tangential it points in the direction of tangent as well. Okay. Yes or no? Okay. Now, if I ask you, suppose a particle is moving with non-uniform circular motion along a circle. So what is the value of AC? Simply consider the value of centripetal acceleration. Is it same or is it variable? The value of AC for a non-uniform circular motion. Okay, Samvidhi said same. Anyone else? Okay, it will be better if I write down the expression, that is V square by R. So centripetal acceleration is V square by R. R is constant since it's moving with for a particular circle. What about V? Is V same? V is not same, right? At point A, since the speed is less, so we have less centripetal acceleration. At point D, since the speed is larger, so centripetal acceleration will be large because it only depends on the speed square by radius. So it depends on speed as well. So since speed is changing at different points, so centripetal acceleration's magnitude will also differ. Differ in that sense, it's since a v square part, so v square will depend, it will less or more depending on the speed at that point. But one thing that I can always be sure, that is centripetal acceleration always points towards the center. The magnitude may changes depending on the speed, but direction will always be towards the center. Okay. Okay. So centripetal acceleration can change magnitude in non-uniform circular motion. However, for uniform circular motion, since speed remains constant, so in uniform circular motion, the centripetal acceleration does not change. Another thing that gives us, that is the resultant acceleration. You see, in uniform circular motion, what happens? There are two acceleration. One acceleration that is AC towards the center, and a tangential acceleration that is towards the tangent. So these two are kind of perpendicular. So that's the reason in uniform circular motion, there comes a resultant acceleration. So resultant acceleration, in that sense, it will be AC plus AT. Since these two are vector, they have 90 degrees in between them. So it basically gives us AC square, or more like magnitude of resultant acceleration is simply AC square plus AT square. Because the AC is perpendicular to AT. Okay. And it has another form, that is AC has a form of V square by R square plus AT square. So it will be somewhere in this direction, resultant. I'm just guessing because we just have to complete the parallelogram and that's the direction. Here it will be centripetal acceleration in this direction. This action is this direction, so basically it will be somewhere in this direction. So the resultant acceleration does not have any specified direction. Here it points in this direction. Here it points in this direction. So both the resultant acceleration and the tangential acceleration, the direction we cannot say anything. But as for centripetal acceleration, we can say it's always points towards the center. Okay. So these are all for like centripetal, uniform and non-uniform circular motion. The problem based on uniform and non-uniform circular motion, at least in this chapter, is really simple. All will be more like directly plug and check all the equations we have derived, nothing more. So do practice and then let us know if there is any other problem or not.